Hello everyone. The topic of discussion of this video is the minimum spanning tree. The definition of a minimum spanning tree goes like this. A minimum spanning tree of an undirected graph G, that is we are focusing only on undirected graph, is a tree formed from graph edges that connects all the vertices of the graph at lowest total cost. Essentially, we will be finding a tree from a graph such that the edges of that tree will have a minimum total cost and the edges should connect to all of its vertices. A minimum spanning tree exists if and only if the graph is connected. We know what is a connected graph. A connected graph is a graph where we can go from any vertex to any other vertex. The condition for having a minimum spanning tree is the graph should be connected. The minimum spanning tree is a tree because it is acyclic, because in a tree we will not have any cycles or loops, and it is spanning because it covers every vertex, because we will have to cover all the vertices of the graph, and it is minimum because the total edge cost is minimum. So these points justifies the name of the structure, that is minimum spanning tree. And notice that the number of edges in the minimum spanning tree is the number of vertices minus 1. We have here a graph which is a undirected graph which has got 7 vertices, and it is a connected graph where we can travel from any vertex to any other vertex. In the second figure, the minimum spanning tree corresponding to this particular graph is given, where you can see that all the edges are connected at minimum possible cost, and you can also note that the number of edges in the minimum spanning tree will be the total number of vertices in the original graph minus 1. So initially we had 7 vertices in the original graph, and if you count the number of edges in the minimum spanning tree, it will be 6. Okay, 1 2 3 4 5 and 6. All right. And we have to understand a basic difference between the shortest path and the minimum spanning tree. In shortest path, given a vertex, you have to find what should be the smallest distance and what should be the path with smallest distance to reach that particular vertex from a given starting point. But in the case of a minimum spanning tree, we are not concerned about from which vertex we are reaching a particular vertex, but in effect we have to get the sum of all the cost of each of the edges to be as minimum as possible. Imagine that if you examine this vertex v5, the shortest path that we can have from the vertex v1 will be v1, v4 and v7, and the total cost of that path will be 1 plus 7, which is 5. But if you look at this minimum spanning tree, we are not concerned about that shortest path to reach the vertex v5, and if you want to reach the vertex v5 in this spanning tree, you have to start from v1 to v4, then to v7, then to v5. If you look at the cost of that path, then it is 1 plus 4 plus 6, which is 11, compared to the 8 in the original graph. But if you calculate the sum of all edge cost, it will be the minimum one. My aim is the sum of all edge cost should be minimum as possible. So this is the main point that we need to keep in mind while we discuss the differences between a shortest path and the minimum spanning tree. One of the several applications of minimum spanning tree is if we want to wire a house with a minimum of cable, then minimum spanning tree problem needs to be solved. We will have to draw cables from one starting point to some other junctions in a house wiring. So we will have several solutions, but we have to come up with a solution such that the total amount of cable used should be minimum. You can also use the concept of minimum spanning tree when you want to plan roads that connects different places of a city. If the first graph shows all the possibility for having roads, and the minimum spanning tree will be giving us a solution such that we will be connecting all the places in the city at minimum cost. It will connect all the places in the city, but it will be at the minimum cost. Okay, so these are the applications of a minimum spanning tree. And now there are two basic algorithms to solve this problem. The first one is the Prim's algorithm, and the second one is the Kruskal's algorithm. We'll be focusing Prim's algorithm in this video, and we will describe about Kruskal's algorithm in the next video. Now let's turn our attention to the Prim's algorithm. I have listed the Prim's algorithm over here. This algorithm is exactly the same as the Dijkstra's shortest path algorithm, but it differs only in these two lines. Here, rather than comparing the presently existing distance with the total distance from the starting vertex, we will be comparing only with the edge cost. If the already existing distance is greater than the edge cost, then we will assign the distance to the edge cost. Okay, this is the only difference that you need to notice while running this algorithm. Here I have given a graph. This is a connected graph as well as an undirected graph. Here we have to make some initialization for all of the vertices. First we have to assign the norm of each vertex to be false. I'll be writing 0 instead, and the distance of each vertex to be the maximum possible value. I will write infinity in the description, and the path of each variable should be assigned to null. I will be writing 0 for simplicity. Now in the beginning, the starting vertex should have a distance of 0. This starting vertex is the root of our minimum spanning tree. Okay, so I will make this initialization with the help of this table. Now we will be running an infinite while loop. Now we have to pick the smallest unknown distance vertex. All vertices are unknown and the smallest one is v1. Okay, and we have to check whether that vertex is null or not. That vertex is not null, so we have to assign the norm of that vertex equal to true. So here in this case we will be selecting v as v1 because v1 is the unknown vertex and which has the smallest distance so far. Then we have to assign the norm of that vertex to be true. So I'll be writing norm of that vertex to be true. Now we will run this for loop. In this for loop, we have to consider each adjacent vertex of the vertex v one by one. So we will do that. So here we have v as v1. v1 has got 3 neighbors, v2, v3 and v4. So the possible values of w would be v2, v3 and v4. Now we will check whether those vertices are unknown. If it is unknown, we will make these comparisons and assignments. So the neighbors v2, v3, v4, all of them are unknown. Now we will make the comparisons. From v1 to v2, the edge cost is 2. The already existing is infinity. We have to change it. We have to change this one also, and we have to change this one also. The new distances will be 2 and 4 and 1. We had to make the changes in this table as well. So we will be changing these 3 values and we will be updating these vertices. So v2 has a distance of 2, v3 has a distance of 4 and v4 has a distance of 1, and all of them are referring with respect to the vertex v1. Now we have completed the case of the vertex v1, so I can remove these values. Okay, now we have to pick the next smallest unknown distance vertex. So these are the unknown vertices. The smallest one goes for the vertex v4. So my v will be now v4. Now we have to assign that vertex to be true because the vertex is not null. So I will be assigning the known status of that vertex to be true. So this value has to be updated to 1. Okay, this is the vertex that we are considering. v4 has got 6 neighbors, v1, v2, v3, etc. up to v7. As per this condition, we do not want to consider the vertex v1 because we have to consider an adjacent vertex only if the known status of that vertex is false. Here v1 is known, so we will not be considering that. So the possible values of w would be v2, v3, v5, v6, v7, that is v2, v3, v5, v6 and v7. Now the presently existing distance with v2 is 2, the edge cost is 3, so there is no need of updation. The presently existing distance for the edge cost is 2, so we will have to update it. So this would be 2. Now the presently existing distance to v5 is infinity, the edge cost is 7, so we can update that also. Now for v6, the presently existing one is infinity, the edge cost is 8, that can also be updated. And the presently existing with v7 is infinity, the edge cost is 4, that can also be updated. Okay, so we have changed the distance variables of the vertices. V2 is unchanged, V3 is changed, V5 is changed, V6 is changed, V7 is changed. So for V3 the distance is 2, it is with respect to the vertex V4, and to V5 the distance is 7, that is also with respect to the vertex V4. To V6 the distance is 8 with respect to the vertex V4, and to V7 the distance is 4, that is with respect to the vertex V4. Now we have done with the vertex V4. Next we have to pick the smallest unknown distance vertex, and in this table you can see that the smallest unknown distance vertex has two candidates, V2 and V3. So we will be arbitrarily choosing the vertex V2. So I am choosing the vertex V2, and then I will be assigning the known status of that vertex to be true. So this is written as 1, that is we have selected V2. Now if you look at the neighbors of V2, V2 has got 3 neighbors, V1, V4 and V5, that is V1, V4 and V5. Out of them V1 and V4 are already known, so we do not want to consider it because this condition is not true. Then we will be considering only the vertex V5, and if you look at the vertex V5, as the presently existing distance is less than the edge cost, we will not make an update. Okay, so we have done with the case of V2. Now we will have to select the next smallest unknown distance vertex. So the unknown vertices are V3, V5, V6 and V7. Out of them V3 has got the lowest distance, so we will be choosing V3. And I will update the known status of V3 to be true. So this will be 1. Now I will look for the adjacent vertices of V3. V3 has got 3 adjacent vertices, V1, V4 and V6. So the adjacent vertices are V1, V4 and V6. Out of these 3, V1 and V4 are already known. You can look at this table. V1 is known, V4 is known. So I do not want to consider these 2 vertices. The only vertex I need to consider is V6. And the distance that is presently there with V6 is 8, but the edge cost from V3 to V6 is 5. So I can update this 8 with the new value 5. So I can remove this 8, then this will be 5 now, and I will be making the corresponding changes in this table as well. For V6 the distance is 5 and it is from the vertex V3. So this will be 5 and here it will be V3. With V6, thus we have done with V3 also. Next I have to look for the smallest unknown distance vertex. So among these the smallest unknown distance vertex is V7. So my V will be V7. Then I will update the known status of that V7 to true. So this value would be 1. When you look at the vertex V7, V7 has got 3 adjacent vertices. One is V4, the other one is V5, then V6. So the candidates for W would be V4, V5 and V6. Okay, out of them V4 is already known. We have to focus on V5 and V6. The presently existing distance to V5 is 7. The edge cost from V7 to V5 is 6. This value is greater than the edge cost, so we can make an update. So I will be changing this value, then I will write the new value to be 6. I will be making those changes in this table also. So the distance to V5 is changed and the path is changed. The new distance is 6 and the path is from V7. So we have done with V5. Now if you examine the vertex V6, the presently existing one is 5. The new edge cost is 1. As this one is greater than the new value, we can make an update. So I can change this value 5 to 1. Then I can make that change here also. That is to V6, the distance will be 1 and it will be from the vertex v7. So this is 1 and from v7. So we have done with the case of v6 also. Now we have to pick the smallest unknown distance vertex. The smallest unknown distance vertex is the vertex v6. So I'm considering v6. Now I will update the known status of v6 to be true. So I'll be changing this value 0 to 1. If we consider the neighbors of v6, v6 has got 3 neighbors, v3, v4 and v7. So the neighbors of v6 are v3, v4 and v7. Now out of them v3 is known, v4 is also known and v7 is also known. So we don't need to make any update. So we have done with the case of v6 also. Now the last unknown distance vertex is v5. So we will consider that vertex v5. So the vertex v will be now v5. Now I will have to update the known status of v5 to true. So this value will be 1. Now we have to look for the adjacent vertices of v5. v5 has got 3 adjacent vertices, v2, v4 and v7. So the adjacent vertices are v2, v4 and v7. And out of them all the vertices are known. If you look at this table, that is v2 is known, okay, v4 is also known and v7 is also known. Now if you pick the next smallest unknown distance vertex, we do not have any unknown vertex, so this will be giving us the value null. Then this loop will be breaking, so that is the end of the process. In order to generate the minimum spanning tree, we have to consider each of these vertices and its previous vertex. Okay, so the root of the spanning tree will be the vertex v1 because it doesn't have any previous vertex. Then there will be an edge v1 to v2, an edge from v4 to v3 and v1 to v4, etc. So the edges would be v1 comma v2, v4 comma v3, then v1 comma v4, next is v7 comma v5, next is v7 comma v6, then next is v4 comma v7. Okay, so these are the edges in the spanning tree. First we will draw v1 v2. This is v1 v2. Next one is v4 v3. So this is v4 v3. Then v1 v4. So this is v1 v4. Then v7 v5. This is v7 v5. Then v7 v6, v7 v6. And the final one is v4 v7. So this is v4 v7. Okay, then you can see that the vertices that is connected using this green line makes the spanning tree. So you will find that this makes the spanning tree because if you calculate the sum of all the edge cost, that will be the minimum one. Okay, one thing you need to notice is this is not the only solution for the minimum spanning tree. You can have different solutions for the minimum spanning tree depending on in which order you are taking the adjacent vertices. Okay, so your aim is to find one of the solutions. So I hope the idea is clear. Thank you.